Okay, so we've talked about matter. This chapter is about matter and energy, and we talked about the matter section, and now we're into talking about energy. We use the word energy in science a little bit differently than we do in everyday life. But I think we can all understand that energy is a very significant thing in the universe. The way scientists define energy is the capacity to do work. And we also have a specific definition of work. Work is the result of a force acting on a distance. So if I take this pen and I lift it up off the table, I have exerted a force through a distance. I'm opposing the force of gravity. I have done work. Okay, in everyday life, work is generally something that's unpleasant or something that you're getting paid for. But actually, things that you do just because they're fun are also work. Anytime you oppose a force through a distance, you're doing work. And so energy is the ability or the capacity to do work. And what's important for us to understand in chemistry is that the behavior of atoms and molecules is driven by energy. It all has to do with energy, and so understanding energy, of course, is then very important for understanding chemistry. So we talked about how matter is conserved, energy is also conserved. So we have the law of conservation of energy. Energy is neither created nor destroyed. So the result of that is that the total amount of energy in the universe is constant. We're not having energy coming in or going out. It's a constant amount of energy. But that energy can be changed and move around quite a bit. So we can change energy from one form to another, and energy can be transferred from one object to another. So there's a lot of moving around of energy, but we can't create energy. There are different forms of energy. And again, I'll apologize for these slides. I'm not going to read them all to you because some of them are just straight out of the book, which is not how PowerPoint is supposed to be. So I'll try to just highlight things. There are two main types of energy. There's kinetic energy and potential energy. And it's important to understand them. Kinetic energy is energy of motion. When something is moving, it has kinetic energy. Potential energy is a form of stored energy. It's associated with position or with composition. So if I lift this pen up above the table, it now has potential energy because if I let go of it, it falls. As it's falling, it has kinetic energy. So when I lifted it up, I was giving it the potential to move and have kinetic energy. So those are the main two kinds of energy we talk about in chemistry. We also sometimes refer to electrical energy, and that's just the energy associated with the flow of electrical charge. Thermal energy has to do with, it is a form of kinetic energy. It has to do with the movements of the particles. When a substance is warmer, it has more thermal energy. When it's colder, it has less. And then chemical energy is really important, and that is a form of potential energy that is stored in how the particles are connected to each other, stored in chemical bonds. Energy is something that we can measure, and to measure something we need units. Okay, and the metric or the SI unit of energy is the joule. It's spelled Joule, and the abbreviation is a capital J. And it's named for somebody whose last name was Joule, and he did some important work with regards to energy. And so that one's kind of a strange unit you might not have heard of. The other one that we use is something you've heard of. It's the calorie. We talk a lot about, this has so many calories. But the calorie that we use in science is not the same. We'll talk about that other calorie in a minute. The calorie we use in science is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And it's actually quite a small unit of energy. There's a relationship between the calorie and the joule. 1 calorie is 4.184 joules. So a calorie is larger, about 4 times larger than a joule, but they're still in the same ballpark of size. Now the calorie you're familiar with is the nutritional calorie. The name of that calorie has a capital C. Its abbreviation is capital CAL. We think of it as the big calorie. It's actually a kilocalorie. It's 1,000 calories. So 1 calorie in terms of, 1 nutritional calorie in terms of your food is enough energy to raise the temperature of 1,000 grams of water by 1 degree Celsius. So it's much, much bigger. And another unit that's sometimes used, the electric company uses kilowatt hours. I'm not sure why your book sticks that in there, but it's in there. We don't use that in science. So this is a useful table showing the relationship between these units. This one, 1 calorie is 4.184 joules. I'm not going to make you memorize that, but you'll save yourself some time if you memorize that, because that one gets used fairly often. The nutritional or dietary calorie is the same as a kilocalorie, and so that's something that you should just remember. It's actually a kilocalorie. The kilowatt hours, I don't think we're going to use that really. There might show up in a homework problem, but if you need it, there's the conversion factor. So we need to learn how to convert units, and this is the same concept we worked on in Chapter 2. It's just we're using different units now. So here's an example. The combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? So we're going to apply the same process we've been doing. We're going to look at that and we're going to say, okay, well, there's one number in there. Let's write that down. 512 calories. That's where we're starting. That's the only number that they gave us. And then the question is, where are we going? What do they want us to find? Well, the question is, how many kilojoules? So kilojoules, and we use the metric prefixes with joules just like we do with grams and milliliters. And so then we know what we're starting with, we know what we're trying to find, and then we have to ask ourselves, how are we going to get from calories to kilojoules? Did that table give us a relationship between calories and kilojoules? No, it didn't. It gave us calories to what? To joules, right? So we could go calories to joules, and then joules to calories is just using metric prefix conversions. So anytime you just have a base unit and a prefix on that same unit, it's just a matter of applying the prefixes. So this has two arrows, that's what those are called. 2 arrows, and so we're going to have 2 fractions in our equation. So 512 calories times and a blank times and a blank equals. We look at the path we wrote out, calories to joules to kilojoules, and in the numerator we write calories to joules to kilojoules. Then we put the previous unit in the denominator because we want those to cancel out. We'll put joules down here. We want those to cancel out. And now we see we've got it set up so that we're going to end up with a unit of kilojoules at the end. Now we look for numbers. So you don't have to do them in order. You can do them in whatever one seems easier to you. Here's this metric one, kilojoules per joule. So I need to remember what kilo means. Kilo means 1,000 or 10 to the 3. So kilo is on the top here. So I'm going to put what it means on the bottom. If you're following my system, you never put the number with the prefix. Okay? That's if you're following my system. There's other ways to do it, but I'm not going to show you those. 10 to the third. And that's makes it hard for us to think about on our calculator, so that's 1 times 10 to the third. 1 kilojoule is 1,000 joules. So then over here what we need to do is we need to go back to that table, or to remember that 1 calorie is 4.184 joules. So we have 4.184 joules equals 1 calorie. The number and the unit on one side of the equal sign will be on one side of the fraction line. And the number and the unit on the other side of the equal sign will be on the other side of the fraction line. So now, I forgot to get out my calculator. I forgot to bring my calculator, that's lovely. Okay, cell phone to the rescue. You can't use your cell phone on an exam, but it sure comes in handy in a pinch. So 512 divided by 4.184 divided by 1 EE3. And my calculator tells me 0.1223794, and that's going to be kilojoules. And hopefully we recognize that's too many digits. How many significant figures should this have? Well, we've got multiplication here. So this one has how many sig figs? 3. And this one has 4. And this one, this is exact. Okay, any units with the metric prefixes just going from one unit to another, those are exact. So we've got 3 sig figs and 4 sig figs. The smaller number is 3. So we're going to round this to 3 significant figures. 0.122 kilojoules. And that's our final answer. Any questions? Yes?
How could we divide the 22 times 512 times the 4.184 and then divide the 1 times 10 to the third power? Because you said divide.
Did I say divide?
Yeah.
I am sorry. I said divide as I was pressing the times key. Yes, that's 512 times 4.184 divided by 1,000. Did I come up with the right answer, though? No? Okay, this one's getting edited. Good grief. Okay, we're going to go back. Just because I can. You can't. Well, the lesson here is that teachers are human and we make mistakes. And I'd like to say I did that on purpose to see if you're paying attention, but I didn't. 512 times 4.184 divided by, oh yeah, that's way off. Okay. That is not what I wanted to do. Are you serious? What the heck did I do? Okay, phew. Scared myself. Okay, so 512 times 4.184 divided by 1 EE3, and we get 2.14. Is this looking better? 208 kilojoules. We have 3 sig figs in the 512, 4 sig figs in the 4.184, and an exact number in the last term. So we're going to round this to 3 significant figures. And there's our final answer. Any questions this time?
I have a question.
Yes.
How did you get the equals 4.184? How did you get that?
I got that from this table.
Oh, okay. Thank you.
Any other questions? Okay, so we did that one.